much for the invitation, and yes, we are close neighbors here in Neckars. And actually, I feel like perhaps we're closer neighbors beyond just spatial proximity, but also scientific proximity. And perhaps this talk will inspire some of you, or maybe you know an answer to some of the questions that I hint upon, and I really would like to discuss with everyone here in the room if they have interest on problems that I will discuss here today. Okay, so also, I guess there's chalk here, right? So most of the talk will be here, but I'll probably have to go on the board to maybe fill in a few details at some point, and if you have questions too, just stop me at any point. All right, so the outline of this talk, basically there's four main things that I want to touch upon. First is I'm going to provide a brief survey of some of the mathematical formalism of finite dimensional quantum mechanics. So of course, like the whole formalism of quantum mechanics is a massive topic. So I'm just going to try to sum it down to just a few slides and just to highlight the essential pieces that we need for this discussion. And of course, it helps quite a bit that we're dealing with finite dimensions, and everything is just in terms of finite dimensional vector spaces. So it's very nice. Then I'm going to discuss the general framework of quantum resource theories. So this topic itself, quantum resource theories, is a very trendy topic right now in the quantum information field. And it gets its origin from the study of entanglement. So as we'll see, quantum entanglement provides like the prototypical example of quantum resource theory. But since then, there's been a proliferation of other quantum resource theories. I'm going to describe some of them. But they all are inspired by this spirit of studying quantum entanglements. And what I'm going to talk about are just some general features that are common to all of the quantum resource theories in the literature today. In particular, I'm going to describe some concepts of resource measures and resource transformations. And then finally, I'm going to provide some specific examples in the study of entanglement and coherence theory. Okay. All right, so mathematical structure is the background that we need. So first, just the basic postulate that we have when we're trying to sit down and write out a theory of quantum mechanics is that every quantum system can be assigned a Hilbert space, H, and this Hilbert space is called state space. So for our purposes, again, this is a great simplification that we're going to be dealing with finite dimensional quantum systems. So here, our Hilbert space, you can just think of as just a complex vector space of finite dimensions here. And if we want to talk about multiple systems, then the next postulate that comes in is we build up more parts to a system by taking the tensor product of vector spaces. So in this example here, we have n subsystems, A, B, C, all the way up to n, and if we want to describe the full joint system, we will take the tensor product of the individual subspaces. Right? So sometimes the subsystems are known as the reduced state spaces, whereas the full state space is called the joint space. Okay. All right, so that's sort of the first part of the structure. Now we will discuss how to describe physical states in a quantum system. So physical states are described by density operators that are acting on our state space. Right? So what I mean by a density operator here is if H is our vector space and then we let L be the set of linear operators acting on H, then a density operator is any linear operator that satisfies these two properties. So the first is that it's non-negative, which means its eigenvalues are not negative, and Hermitian as well. So it's Hermitian non-negative. And the second is that it's trace 1. Right? So these are the two defining properties of a density matrix. And the point is that any operator satisfying these properties represents a valid state of the quantum system. So we have this nice correspondence between objects that are acting on our vector space and physical states that can be realized in nature. Okay? So as long as if you give me any operator that satisfies these properties here, it's a positive operator, trace 1, then in principle I could go into the laboratory and cook up a state that corresponds to that operator. All right. So just for some terminology here, we will denote the set of density operators acting on our state space by this DH here. Okay, so the D is density operators. Now, if we wanted to understand the structure here, the set D is a convex subset of L. It's actually a positive cone, right? Because it's all the elements there are positive, and any linear combination of them will satisfy. Oh, I'm sorry. If we drop if we mandate trace, then it's not a full cone. But if we drop the trace, it's a subset of the positive cone. Okay, so here's an example for us here. For a bipartite state space, so we have two systems, A and B. So what I've done here, I've taken our density operator and I've just expressed it as a linear combination of these Mi and Nj. So you can just think of these as a basis for matrix space. All right. So this is a finite dimension. So I have dA squared dimensions or matrices here for system A and dB squared matrices for system B. And so these Mi span the space A and the Nj span the matrix space B. So I can take any element in that matrix space and write it as a linear combination. All right. And then for this to be a density operator, though, we have to have positivity. So positivity means that if I act on by any side and I take the inner product there, then it should be non-negative. Right? So I take any side in the joint state space, and I contract it with my operator, then I get something that's non-negative. And then the other condition is the trace. So the trace is a linear operator, so I can bring it in and just take the trace of these basis elements there, and that should sum up to 1. Okay. Alright, so that's just an example. Alright, now so much for the states. Now we're going to talk about the dynamics, and this is the other half of the coin here. So in general, we talk about a quantum operation, which is any physical process that maps density operators to density operators. Okay, so in particular, this map is it's positive and it's a trace preserving map. So what I mean by positive is that if I input a density matrix, so I input some positive operator, and then I act on it by my map E, what I get out is a positive operator. Right? And of course we should demand this, because if it's really some physical process, then if we input something that a physical state, we should get something out which is a physical state as well. So that's the condition of positivity. And also it should be trace preserving. Okay? So it should preserve the trace. Again, if I put in a physical state, I act on it, what I get out should be a physical state, and we know all physical states are trace 1 objects. So it should have these two properties. But actually we should demand something a bit stronger. We should not only demand positivity, but we should also demand something known as complete positivity. Okay, so what complete positivity says is if I have my map here, E, and I just act on a subsystem, all right, so I'm acting on system A, and I'm doing nothing to system B, that should still preserve the joint density matrix AB. Okay, so again, you can think of this as, so let's say Messiah and I share a state. Say I'm A, he's B, right? So we have some valid state, but I'm not able to go into his laboratory and act on his part of the state. So all I can do is act in my local laboratory here. So all I'm able to do is just apply a local map here, and Messiah does nothing. He just sits there and listens to the talk, enjoys it immensely. And then what comes out at the end of it should be a valid state, right? So we demand that it's a positive operator, just through my local action, and that the trace is preserved. Okay. So this property is this notion of complete positivity is stronger than just this notion of positivity. All right. Okay. So every quantum operation, this is sort of the main take-home message of this slide. Every quantum operation is represented by a trace-preserving, completely positive map, or a CPTV map. All right, any questions at this point? It's interesting, actually, that if you were to sit down and try to work with completely positive maps versus positive maps, these are actually much easier to work with than just positive maps. So you think if you add this restriction, this extra constraint, that would make it more challenging, maybe, but it actually makes it easier. And fully characterizing positive maps it's a challenging open problem, whereas complete positivity, there's a nice mathematical characterization of them.
you still positive means or eigenvalues.
All eigenvalues are positive. That's right. Yeah. Okay. And okay, so you can ask the question. I mean, why do we demand positivity? And the reason has to do with the way we physical interpretations. So one thing, if you have a state and you make a measurement on the state, the expectation value of that measurement is given by something that looks like this. So it's like an inner product type there. And so what you demand is that you want to be able to assign some physical meaning to expectation values, and so you need those to be positive or not negative. Okay. So it ultimately comes back to it's a physical interpretation. Okay. So some important examples here. This is what I was trying to describe. So one example of the CPTV map is a measurement map. Okay, so in quantum mechanics, any collection of positive operators here, so again, these positive means that they have non-negative eigenvalues, and they sum up to the identity, so this is the identity operator on our space H, represents a quantum measurement. So what I mean, again, by represent, I mean that if you cook up if you give me some set of operators that satisfy this property, they're positive and they sum up to the identity, I should be able to go into the laboratory and perform the corresponding measurement. So there's a physical correspondence to this mathematical object. And I want to try to describe this in terms of the CPTV map. And the way this can be done is what's known as a measurement map. So it's a map that's taking density matrices on our space H to the set DCK. So big K is the number of elements I have in this set here. And the way the map works is I just take the inner product between pi k and rho, or I just take the product and then take the trace, and then what I pop out is something that looks like this here. So I'll just introduce what I'm talking about here. So you can think of k, this is like a column vector. So it's 0, 0, it has 1 here. So in the kth row, you have a 1. Okay? This is sometimes called a ket. Right? So and then the associated is a bra, and this is the row vector, which is 0, 0, 1, 0, 0. So we have the ket and we have the bra, and then if we want to form this object here, what we do is we just do ket bra. Okay, so k now this is just matrix multiplication, which is it's the beautiful thing about this. So I have a column vector, which is the ket there. I have a 1 here, and then I have the bra vector, which is a 1 there. And then so what I get out is a matrix, right? That has just a 1. It has zeros everywhere else, but it has a 1 on the kth row. Or sorry, the kth column and the kth row. Okay, so it's a rank 1 matrix, diagonal matrix is the 1 at the kth spot. So it's probably one of the simplest type of structure that you can get. And the point is that what this measurement map does is it takes our state rho and it maps it to this operator here, k, with some probability. And we interpret this weight here as the probability of obtaining outcome k when measuring the state rho. Okay? So k here, this is like an index that's telling us what the measurement outcome was. Or another way of thinking about it is that it represents the state of some classical measurement device reading outcome k. So if, in principle, when I'm doing this in the laboratory, I'm making a measurement, I'm having some computer readouts that's saying, oh, the electron is in this half of the box, or something like that, right? And so what this here is representing is the state of some classical measurement device reading. And so then this is the probability of that classical measurement device being in the particular state reading outcome k. Is a way to think of this. Okay, so this is known as a measurement map. And now you can see, coming back to the question of positivity, is you want to interpret this as a probability. And so if rho was not, it didn't have positive eigenvalues, then you would have a negative, could have a negative here for certain measurements, and then your interpretation would be off. So the positivity on rho is crucial here. And also you can see that this condition here, that when we sum over the pi k's, if they give us back the identity, guarantees that the outcome here, the output here is trace 1. So if I take a trace of the right-hand side, what I end up doing is I just sum over the pi k's. I know the pi k's give me the identity, so I just have the trace of rho, but trace of rho is 1, so the right-hand side is trace 1 object. So everything fits together nicely. Okay, another example is the partial trace. And so what the partial trace does is it allows us to go from a joint state to a reduced state. Right? So if here's our row AB in this joint state space, and I want to know, again, coming back to Messiah and me, so we have this joint state row AB, and I just want to describe the state in my lab. I don't really care about what's going on in his lab. And so what I want to do is I want to trace him out. I want to throw him out of the way. And all I want to do is just talk about the state in this laboratory. So mathematically, we describe this as a map that's going from the joint state, AB, to row A. And the way this is done is using the partial trace. So again, we start off with our density matrix here, which I've expanded in a tensor matrix product basis. And then I apply the trace, and I'm just going to trace on the second operator here. Okay, so this is sort of a linear operation, right? I bring in the trace and I just trace on nj and I multiply that by mi. And we started off with some sum over ij here, so I could just combine the sum into j into 1 and I get a new coefficient, which then is row A here. So this would be the description of the state in my laboratory. And you just get it from using this CPTV map, the partial trace. Okay. All right, any questions on this stuff? Because then this is like the basics. All right. So this is the main topic of the talk. It's on quantum resource theories. And so I'm going to just define what I mean here first. Well, first let me motivate it a bit before I get to the definition. Okay, so we just talked about what the CPTV map and these maps describe what is physically possible, right? And I said if you give me a completely positive trace preserving map, in principle I should be able to go in the laboratory and do it. Right? That's this idea between the correspondence between mathematical objects and physical objects. But in practice, the full arsenal of CPTV maps is not accessible to the experimenter. Okay, so it's a very idealistic world to think that I can implement any CPTV map that I choose. More realistically, due to experimental limitations or environmental circumstances, I won't be able to perform the most general processes that nature allows. Right? So for example, you can think of a quantum computing engineer. Perhaps they can only use certain type of gates on their circuit board. Right? I mean, they're not able to, for whatever reason, cost, or they just don't have the tools to perform an arbitrary gate on their board, so they are limited to what they can do when they're building their quantum computer, gate-wise. Or another example, you can imagine you have two individuals who are wanting to communicate with one another, but they're located far apart, and they don't have a fully shared reference frame. So what that means is perhaps there's some coordinate system, and what I call up, the other observer doesn't quite agree with that. We have a different agreement in our orientation of our coordinate system. And if that's the case, then there are really only a limited number of degrees of freedom that we can use to encode our message. Okay, if we don't share, if we are unable to coordinate our reference frames, then we can't fully use all the degrees of freedoms in our system. So there's some limitations there if we want to communicate successfully with one another. And what a quantum resource theory does is it provides the mathematical framework to model the physics in these restricted settings. Okay, so that's the motivation. And so here's the definition. So we'll say that a quantum resource theory, what it is it's an assignment, such that it associates every Hilbert space H with a tuple. And so FH and OH, where FH is a collection of density operators that are acting on H, and OH is a collection of CPTV maps acting on the set of density operators, such that, and this is the key property right here, all right? So it's that if E is a map belonging to this set O here, then if I act on any row in F, I should get out another element in another set F. Okay, so O should map the sets F to F, all right? here's a picture. So for every Hilbert space, remember there's an assignment, okay? So for H, I'm assigning a set here, FH, and for H prime, I assign another set here, FH prime. And so the requirement here is that my map E must map this subset here to this subset here, okay? What's happening outside of the subset is arbitrary. It doesn't really matter, right? I could take an element here, I could map it outside, or I could map from outside F to inside F. But the constraint is that it must map what's inside F to something that's inside of F here. For every map E that's in this set O. Okay, so that's the mathematical picture, but the interpretation is that the states in FH are called free states, okay? And the operations in OH are called free operations. So what we think about is what's in here, these are easy to generate. These are states that we get for free, all right? And then the E's that are in our set, oh, these are operations that we can perform for free. These are operations that are easy to perform. And in order to be a quantum resource theory, what we demand is that our free operations, when acting on the free states, preserve the set of free states. Okay, we can't take a free state, act with a free operation, and get something that's not for free. That's not free. So, and any state that's not in this set of free states is called a resource state. Right? So any state that's outside here is a resource. And it's called a resource state for understandable reasons, because we can't generate any state that's outside of F using the allowed operations. So we can really think of it as a resource. It's something that we don't have access to, nor can we create using our allowed operations. Okay, this is the crux of it, and
There's a question.
yeah.
Would it make sense to think about an enrichment of this definition where instead of just free and not free, you had a grading of free, grade 1, grade 2, grade 3, and on out, eventually taking in the whole space?
Yeah, you could do that. You'd want to have a good like physical reason to do that. And actually, I can think of one. Yes, so the answer is yes, you could certainly do that.
Yes, my idea is grading the cost of the non-free things.
Sure, right.
They should have some cost that may vary from one.
Yeah, okay, that's a good idea. Yeah, you could certainly do that. You'd have to be careful though how you're defining cost.
Right.
And it brings in a number of complications.
Yeah.
Do you agree this would be the simplest, right? You're either in or you're out, right? But yeah, and in fact maybe that's a good approach, is to think about a low cost approximation or something like that, right? Yeah, certainly.
But mathematically, this FH is just any subset.
It's any subsets, right? So I drew it here as like a nice convex set, but in general it doesn't need to be. Yeah. All right. It doesn't even need to be a closed set for that matter. But most of the nice physical resource theories, it is a convex closed set. But this is just a very general definition. Okay, so the prototypical example is entanglement. So this gives us, as I said in the beginning of the talk, this sort of motivated the whole idea of finding or describing other quantum phenomena in terms of a resource theory, was the success from quantum entanglement theory. So in quantum entanglement, the free states are convex combination of tensor product states. All right, so again, this is a joint state, rho AB, and I'm writing it as a convex combination, means that there's some probability distribution summing up to 1, and it's a tensor product state. So it's some state psi A that's in the state space A, and another state psi B or omega B in the second state space, and so we take the tensor product of them, and now we take a convex combination of them. So these are the free states in the resource theory of entanglement. These are called separable states. So any state that cannot be expressed in this way is called entangled. So if you want a definition of entanglement, here it is, right here. If you give a density matrix rho, if you cannot express it in terms of a convex combination of product states, it is by definition entangled. Okay, so I mean that's a mathematical definition, but from a resource theory perspective, we can get a bit more of a physical understanding of why we think of these states as being non-entangled. And the reason comes when we consider the free operations as being local operations in classical communication. So these are going to be the free operations for our resource theory. And so what do these consist of? All right, so I'm going to describe this set here just by just drawing a picture. So we have two parties, Alice and Bob, and they're sharing their state rho AB. They're separated from one another, okay? And what will happen is Alice is going to perform some quantum operation in her laboratory, right? So previously I was talking about Masai and me having separated and acting locally. This is the exact same idea. So Alice has her laboratory, she performs some quantum operation, and let's say it involves a measurement that she's doing, and she obtains some measurement outcome M1. And then what she does is she announces it to Bob, and Bob hears this, and then based on this information M1, Bob performs a quantum operation. Okay, but it's a conditional quantum operation. So what he chooses to do, again, there's an infinite number of quantum operations he could do on his subsystem, but the one he chooses to perform depends on the outcome of Alice's measurements. Okay, so it's conditional. Then he makes his measurement, he gets measurement outcome 2, he sends that back to Alice, and now she makes a third measurement that's a function of outcome 1 and outcome 2. And this goes back and forth, right? So it has this very complicated tree-like structure. But at the end of it, so they agree on some protocol. They say after our rounds of exchanging messages, we're going to stop. And what do we get out at the end of the day? What we get out is something that is, again, it's described by a completely positive trace-preserving map. But it has this form here, where everything Alice was doing locally is collected, concatenated into one map here. Everything Bob does locally is concatenated to one map here. And you see the tensor product structure is still remains. So, and the reason is because this is a local map acting on subsystem A, and this is a local map acting on subsystem B. So even though we have this classical communication going between them, the quantum operations are still local. All right. So the key here is that the only information exchange between Alice and Bob is classical. All right? Classical meaning you can write it down on a sheet of paper and send it, or you can put it in a text message. Right? These are the information is classical here, and so then what we want to isolate the part shared between Alice and Bob that cannot be generated by this exchange of classical communication, and that's why we identify it with entanglement. So entanglement cannot be generated in this way. And in fact, you can see that if you just back up here. So here's our separable states. Remember, I said these guys are non-entangled. Okay, and so now I take an LOCC generated map, which has this form here, and I act on the separable states. Right. So, right, so I started off with the separable state, so it's rho AB, pk, sigma k, omega k. And now I act on it with this map that I've generated by this physical process here. So what I end up getting is E acting on rho AB, which is it's linearity, right? So everything here is linear. That's the key idea, is that I can bring this pk here, and now I have this A total on Alice's side. So A total acting on psi k, tensor B total. I guess there's some message here, right? Sorry. M total M acting on omega k, and you can see it, everyone. What's happening here is I've still preserved the tensor product structure, right? So what I'll get out is some new convex combination, so I'll call this pk hat, and some new psi k hat, tensor omega k hat, where this is sorry, the sigma k is just generated by the local map acting on sigma k, and I guess we're summing over m too, so there should be a sum here. Okay, point being is that physical processes described by here are unable to generate entanglement. When you act on a free state, here a separable state, what you get out is a separable state. All right? So that's the general structure of this. Okay. Any questions on this? All right, so I'm going to highlight 3 other quantum resource theories. The first is quantum resource of asymmetry, and actually Borzo here is an expert in this. So if you have any questions of this on this resource theory, you can discuss with him. But the idea here is that you have some group G, and you have a unitary representation of it, UG. All right. And so what you want to just define as your free states are states that have the symmetry of your group G. So precisely what that means is that I define this tau here, which is a group twirling map. So what I do is I take rho and I apply UG to it. Okay. So I conjugate rho by UG, and then I average over the group. And so what I'll get out is some density matrix. And rho will be symmetric under the action of UG if this operation here doesn't change it. Okay, so I'm averaging, and then I get something out, and the free states are those where this action tau leaves it invariant. So it's symmetric under the group action. And the free operations here are maps tau maps E that commute with tau. So I can perform the map E, and then I can twirl, or I can do tau and then perform the map E. So these are the free operations of this in this symmetry. So in this particular case, the resource states are those that lack symmetry, right? So they're asymmetric. That provides the resource. Those are the resource states in this theory. Another example is in quantum thermodynamics. So here, it's a little bit longer to explain what's going on, but you imagine you have your system H and you have some Hamiltonian that's acting on your system. And so the way you define your free states are in terms of the thermal states or the Gibbs states. So at some particular temperature, you associate, you have the Gibbs state, which is the thermal equilibrium state, and it's given by this here. So you just exponentiate the Hamiltonian divided by the temperature. And these are the free states. Okay, so you're allowed to prepare the thermal equilibrium states. And then your free operations are defined as follows. So you bring into here, it's a map that's acting on rho, and the way what you're allowed to do is you're allowed to bring in some other thermal states. Okay, so you can prepare it in your side laboratory, some bath, some ancillary thermal states with some other Hamiltonian H tilde. And then what you're allowed to do is you're allowed to couple your system and the ancillary system with some unitary here that preserves the energy. So it commutes with the total Hamiltonian. All right, so this is sort of like an energy preserving operation. And then what you do is you trace out. So you throw away the bath at the end of the day, and you ask what's happened with my initial state rho. So again, you think of it in the process, you prepare it in the other system B, you prepare some thermal state with respect to some other Hamiltonian. You do some coupling between the two systems that leaves the energy unchanged, and then you just throw away the ancillary system. So those are your free operations in the theory of quantum thermodynamics. Another example of a resource theory is quantum coherence, and I'm bringing this up because actually the last part of the talk will be about this. And so here, this is very simple to understand how this works. So you fix some orthonormal basis for your Hilbert space. Okay, so this is just any basis, some D elements. And then your free states are just the density matrices that are diagonal in this basis. Okay? And as for your free operations, there are multiple proposals for which are the free operations in this resource theory. I say stay tuned because I'm going to discuss one of them at the end of the talk. Okay. And this is just a short sampling, so there are many other types of resource theories that have been developed in the recent years. But the key idea is that what each of these are doing is they're pinpointing some particular feature of quantum mechanics or the quantum system, and they're isolating it in terms of free states and free operations, and they're studying just that particular property in terms of this framework, this quantum resource theory framework. So I really think this philosophy is a very helpful and instructive way of understanding the physics of particular things, because it really allows us to parse out different properties of quantum systems and study individual properties. Okay, so just some general features. So if we have a quantum resource theory, one thing that we might want to do is we want to quantify the amount of resource in a given state. So this may be practical, have practical reasons. Eventually you may want to assign a dollar value to it, right? And you could say one particular state is more resourceful than another, so we're gonna associate a greater cost, and you'll have to pay more to bring it in your laboratory to use. Or, I mean, that's the spirit of this idea. And so what we'll define mathematically is a function phi, we'll say qualifies as a resource measure if it satisfies two properties. So the first is that it's a non-negative function, and the second is that it vanishes for all free states rho. Okay, so this is what we would expect. It's very intuitive. It's just saying that free states have no resource. This phi is, again, the idea is we want to construct a function that is quantifying the amount of resource in our state.
Is it if and only if?
Is it what?
Is it if and only
No, it doesn't need to be. It doesn't need to be, right? It's a good question. And actually, that question is tied into Wesley's question. If you want to have like an intermediate ball around the free states, where it's not quite free, but it has this, it's not the full resource state. So then you might want to relax, or you might not want to have the converse here. So you might want to have a state that is technically not in this inner set, but we would still assign it no resource because it's like it's just too weak, right? Yeah. Okay, and then this is then the crucial property is that our function phi is monotonically decreasing under the free operations. So what I mean is if I take any of my operations that are free and I act on rho, the value better not increase. And this is almost like a consistency condition, right? Because it would be, I mean, it wouldn't make any sense to think of a function as being a measure if I can just increase it for free, right? It would be like dollars growing on trees, right? Just free. I just go in my backyard, I water my plants, and all of a sudden they just start sprouting dollar bills, right? Then the dollar wouldn't have any value. If it was so easy to just create, we could just do it for free, then there wouldn't be any point of assigning any value to dollar bills. So this is that consistency condition there. All right, resource value cannot be increased by the free operations. All right, so I'm going to describe just a few examples of these. So first, all really are based off the idea of a distance. So here's our picture again. We have our free states here, and then we have an arbitrary state rho. And the idea will be to capture the amount of resource in rho by how far it is from the set of free states. That's why I say it's distance based. And so then it comes again. We have to be clear about how we're measuring distance. So there are a few ways to do this. The first one is based on the trace norm. So for an operator, any general operator A, we can define its trace norm just as follows. So I look at A dagger A and I take the square root of it and then I trace it. This is its so-called trace norm. Another way of saying it is it's just the singular values of A. Right? And a crucial property of this norm is that it's contractive under CPTV maps. All right, it's a very important property that if I act on by any CPTV map, I'm not going to be able to increase the trace norm. So it's contractive. All right, and this is the key property that allows us to define a good measure. So the measure is given by this. Call this d rho, and what I do is I have my state rho, and then I take the infimum over all sigma in the free set, and I just minimize this distance here. Right? Very intuitive. So I look at rho, and then I consider all the free states there, and I find the one that minimizes the trace norm distance. Okay, and let's see. So it satisfies the properties because if rho is in F, then I just choose sigma to be rho, and I get that to vanish. And again, it's not increasing under the free operations because it's not increasing because I know when E acts on F, it preserves set F. Okay, and then I also know that the trace norm is contractive under the operation E. So there's two properties that go into this. Again, one is that E preserves F, and the other is that the trace norm is monotonic under CPTV maps. Okay, so this is one particular measure that works. Another, and perhaps this is a bit more physically intuitive, is known as a robustness, resource robustness measure. And so the idea is the following. So I start off with my state rho, and what I'm going to do is I'm going to mix it with some other state, sigma. All right, so this parameter here, lambda, this is like the amount that I'm mixing it by, or rather, wait, what is wrong? Oh shoot, it should be lambda minus 1 minus lambda. Other way around. Forgive me. Because I want lambda to quantify the how much I'm mixing by. So let me just write it down. Okay. So I have my state rho, and what I'm going to do is I'm going to add to it some lambda amount of some other state here. Okay, so you can think of just, here's the state rho, and then I mix it with some other state sigma here. And what I want to do is I want to find the minimum amounts of mixing that I must do so that I destroy all the resource. So it drops me back into the free states, right? And it's called robustness because if it's a very robust resource state, then you have to add a lot of noise in order to bring it back down into the set of free states.
So this is anything over lambda and sigma?
Yes. Yes.
Both. Okay.
Yeah. Yep. Yes, it is. But the measure itself is just lambda. Yeah. Right. And so, okay, it's switched on this on the slide there. But when lambda is 0, then I just have that rho itself is free. So I don't need to mix it with anything because I'm in the set. So this is a robustness measure. And this quantifies the minimum amount of noise that must be mixed with rho to destroy the resource. Okay. All right, I'm just going to move on. Okay, so that's so much for measures of resource. Now when some interesting problems, perhaps the most important problem, is transformation of resources. So the question is, can I go from one state rho to another state sigma by the free operations in the resource theory? Okay, and why is this interesting? Because what it does is it provides an operational comparison between the resource content in two different states. Specifically, if I'm able to go from rho to sigma for free, then rho contains at least as much resource as sigma. And the reason we're justified in concluding this is because any task I can do with sigma and the allowed operations, I can also do it with rho. Right? So if whatever I can do with sigma, I can start off with rho, and then I transform to sigma, and then I do the task. So rho is a more resourceful state in that respect, in a very operational sense. I can simulate whatever I do with sigma, I can simulate it with rho. Right. So in entanglement transformation, in entanglement, the question then is when given two states rho and sigma, when can I convert one to the other by this class of LCC? Right. This is the Alice and Bob discussion, classical communication, local measurements. In general, this problem is unsolved. It's a very difficult problem. However, for pure states, there is an answer. So what I mean by pure states means that the density matrix is just a rank 1 operator. Okay. And so the answer is given by, again, it's given by entanglement measures. So for a pure state psi, we can define what's known as the chi-fan norm. And what you do is you look at, you trace out Bob, so you trace out one of the parties, and then you look at its eigenvalues. So this lambda I down here, this denotes the ith largest eigenvector. Okay, so this is the so-called chi-fan norm. And it turns out that you can show that for every k, this measure, ek, is actually a resource monotone under LLCC. So you're actually you're unable to increase the chi-fan norm of your state for every k. And the very cool thing is that these provide a necessary and sufficient condition for convertibility between two pure states using LLCC. So you can go from a state psi to phi if and only if you have the measure of psi is greater than the measure of phi for each of these chi-fan norms. And I highlight this because it says that resource convertibility is determined entirely by a finite number of monotones. Okay. So in the last 5 minutes, I want to just touch on this topic because this is some work that I've been doing recently. And this is on coherence theory. So again, recall, this is the third example of a resource theory that I gave. So in the quantum resource theory of coherence, free states are diagonal in some fixed basis. So here the PIs are the diagonal elements. And I said that there are, it's open for discussion on what are the free operations. There's many different proposals. One proposal is the free operations are dephasing covariance. So what I mean is the following, that a CPTV map is dephasing covariant in coherent operation if this holds true. Okay, so a picture will suffice. So what I'm able to do is I can commute my map with a measurement. All right, so I start off with rho, I can perform my map, and then I can measure. Or I could do it the other way around. I could measure my system, and then I could perform my map, and I get to the same place, right? So it commutes. So I'm interested in maps that have this property. And what you can see is if your map has this property, actually, it maps the set of free states onto itself. So if I start off with a state that's diagonal in this form, and I perform one of these maps, I'm going to be left with the diagonal states. So it provides the ingredients we need for a resource theory of coherence. Okay. So all right. So it preserves the free states, but what about for resource states, i.e. non-diagonal states? When is it possible to transform one to another using one of these covariant maps? And again, the problem is not solved, but for two-level systems, we were able to derive the answer. So for two-level, it's just a 2x2 matrix, very simple matrix here. And it's a Hermitian matrix, and we can actually assume that all the elements are non-negative. And it turns out that you can determine whether you can convert one to the other using these operations in terms of monotones. So here was the robustness monotone that I described on the board here. And what we define is a new type of robustness monotone, which you can see it looks very similar, except there's a further constraint on this sigma that we're minimizing over. And the constraint is that the diagonal elements of sigma must be the same as the diagonal elements of rho. So that's saying if I just take the difference and I look at the diagonal elements, they must vanish. So now what I'm doing in this new measure here is I'm mixing rho with states having this form, and it turns out that this is also a monotone under these class of operations. So for example, with 2x2 matrix, it has this nice form here. You can compute them. You can do this minimization very simply. It's a non-trivial calculation, but it's not too bad. And what it turns out is that you can go from one state to another under this class of operations, again, if and only if these resource monotones are not increasing. So this is a necessary and sufficient condition for convertibility. Okay, so conclusions. Quantum resource theories provide a framework to isolate certain features of a quantum system, quantify it, and study its dynamical properties. There are a number of open problems involving convertibility of conditions for one state to another. Usually these are very, very difficult, but I think there's slow progress being made on various fronts. And one of the things that excite me and I find very interesting is that the same mathematical structures appear in many different resource theories, even those which seem otherwise unrelated. So I think it was a few months ago, I gave a talk in the physics department on how the same mathematical structures appear in different problems. And this majorization idea appears in many different, majorization, these Keefe norms. Okay, so it's related to the theory of majorization, and that appears in many different resource theories, and it also appears in other areas of mathematics as well. So there's a lot of cross connections between different areas. So for example, by studying the convertibility of states under Dio, in coherence theory, we can learn something about the convertibility of states in entanglement theory. And in fact, I can go into this in more detail, but it's a little bit takes a little bit of time to unpack. But suffice to say that there is connections between the two, and I think we're learning new things by inventing and studying new resource theories. So thank you very much.